Hello. Starting off with Chapter E on the essentials to get us ready to dive into chemistry soon. Just an FYI, we have some homework due this Wednesday regarding just kind of intro to the software system and into the syllabus. Chapter E homework and reading assignment is due on Friday, but hopefully you can get started before then. And then make sure you're doing Chapter 1 reading assignment before class on Monday. Getting into it, we're talking about measurement types. So qualitative are descriptive in nature. We're thinking adjectives. So color, texture, qualitative size, shape, stuff like that. Quantitative observations are involving numbers. So we could either take a measurement and make a numerical value. We would be wanting to use an instrument or device to make our measurement, and that will therefore have some precision or accuracy associated with it. And then we could also have counted values as a quantitative observation. So in this case, I could count how many cats I have, and that would be a quantitative observation. I could also weigh all of those cats and find out what their total mass is. That would be a measurement. Each type of measurement is going to involve a unit. And that's the units we're going to mostly use in this class are the SI units, so basically metric units. And then numerical values, so the number part of the measurement. And that will be based on the scale of the instrument and the precision that you use to make the measurement. So we could have 49 students in the class. The 49 would be the numerical value, students would be the unit, so that would almost be like a counted value, and then 108 days in the semester, so 108 is a number and days is the unit. Anytime we make a measurement, we can have both systematic and random error. So systematic error is in the same direction, so always too high or always too low. This is usually fixable because it's an error in the system. So if you forget to calibrate your scale, then it might always be reading higher than it should be, right? So that's a systematic error that can be corrected. Random error is just based off of a lot of times it could be human error, it could be just error in the instrumentation, and that will kind of average out to the true value. Because it has an equal probability of being either higher or lower than the true value, and that one's actually really hard to correct or find the source of because it is random. When we are talking about the SI units, the unit of length we are going to be dealing with is meters, and we'll use the symbol M for meter. Mass is going to be kilogram, which you might think gram, but when physicists specifically are using mass in calculations, they're going to be using kilograms. So for example, the unit of energy, joules, is a kilogram meter squared per second squared, so kilogram being the base unit there. Time is going to be in seconds. Temperature in Kelvin, and it's not degrees Kelvin, it's just plain old Kelvin. Amount of substance is moles, and electric current is amps, or amperes. Let's call it A. These are going to be really important to memorize, these prefixes, specifically kilo being 10 to the third, centi being 10 to the negative 2, milli 10 to the negative 3, micro 10 to the negative 6, and nano 10 to the negative 9. You will need to memorize those. So using these prefixes, we know that 1 kilometer is 1,000 meters. So we have a lot of meters in 1 kilometer. So it would be correct to say that 1,000 kilometers is 1 meter. Well, that is the opposite of what that is saying. So no. Would it be correct to say that 1 over 1,000 kilometers is 1 meters? So we could divide both sides by 1,000. This side would be 1 then. 1,000 divided by 1,000 is 1. So 1 meter over times or equals 1 over 1,000 kilometers. Yep, that works. If we take 1 over 1,000, that does equal 0.001, so that does work. And we can rewrite 1,000 as 10 to the third, so that also works. When we're thinking about temperature as a measurement, we have 3 different scales. We have Fahrenheit, which we're most familiar with as far as measuring the temperature of like our normal everyday activities. Celsius, which we're also fairly familiar with, and Kelvin, which is less common, measured to like the public. Celsius and Kelvin have a similar scale. So for every 100 degrees of increase of Celsius, you'll have 100 increase in Kelvin. But not so much for Fahrenheit. So for that 100-degree raise for Celsius, you'll have 180 degrees Fahrenheit. So it's scaled quite differently, which makes it kind of hard to compare as far as temperature changes go. The equation to go from Celsius to Kelvin is really nice. It is that Kelvin equals degrees Celsius plus 273.15. You can say the 0.15, or as you start to do it more and more, you'll start to realize that it doesn't make as big of a difference, but do you. So if we have liquid nitrogen boiling at 77 Kelvin, what's that temperature in Celsius? So we're going to plug in this number for Kelvin. So we have 77 Kelvin equals, we're trying to solve for Celsius, plus 273.15. We're going to subtract that over to both sides. And so we get that the change in Celsius, I'm actually going to write that this is the new temperature is negative 196.15 degrees Celsius. So this one's kind of a more straightforward one. I prefer to calculate in Celsius and Kelvin. Notice that you cannot, so absolute 0, which is the lowest you can go, is 0 Kelvin. So you can have negative Celsius in Fahrenheit, but you cannot have negative Kelvin. So keep that in mind. To go from convert between Celsius and Fahrenheit, we have this equation. Fahrenheit equals 1.8 times degrees Celsius plus 32. So a little bit more complicated, different algebra. We're going to calculate the body temperature from Fahrenheit to Celsius. So we're going to plug that in. 98.6 degrees Fahrenheit equals 1.8 degrees Celsius plus 32. So we're going to subtract 32. And when we do that, so we get 6.6. So here we go. We have 40 degrees Celsius. And if you remember, our temperature in Kelvin equals temperature in Celsius plus 273. So we'll plug that in for the Celsius and then add 273. So we get our temperature in Kelvin equals 313.15. If we want to go to Fahrenheit, we're going to do degrees Fahrenheit equals 40 degrees Celsius times 1.8 plus 32. Plug that all into the calculator and we'll get our Fahrenheit is equal to 104.0 degrees Fahrenheit. In this case, we have gallium. Its melting point is 85.6 degrees Fahrenheit, so we want to know what it is in Celsius, and then Kelvin. So we can do 85.6. We're going to use Fahrenheit equals 1.8 degrees Celsius plus 32. So we'll do that guy equals 1.8 times Celsius plus 32. So we're going to subtract over 32 and then divide by 1.8. So when we subtract by 32 and then divide by 1.8, we get our temperature in degrees Celsius is 29.8. So there's part A. Part B, we're going to take that number and add to 73.15. And when we get that, we get 302.95 Kelvin. Okay, so will an increase from 0 Celsius to 100 Celsius feel the same as 273 to 373 Kelvin? We already talked about that. Yes, indeed, it will, because those temperature scales are proportional as far as their increase goes. The melting, that happens to be the melting and boiling points of the water, so it'll be melting point is 0 degrees Celsius or 273 Kelvin. Boiling point is 100 degrees Celsius or 373 Kelvin. Okay, the surface temperature of the sun is approximately 5778 Kelvin. What is that in Celsius? So we'll do 5778 Kelvin equals Celsius plus 273. So we'll subtract 273 from that side, and we will get our temperature of the sun is 5504.85 degrees Celsius. And is negative 300 degrees Celsius possible? Well, if you look at the last couple slides, you'll see that the 0 Kelvin is negative 273 Celsius, so we can't go lower than that, so no. Okay, after we make measurements, we want to kind of determine how reliable they are. So we can do that in the form of precision and accuracy. So precision is how close those measurements are to each other. So the agreement or closeness of measured values. And accuracy is the closeness of the measured values to the actual known value. So we can think of this as being very precise because they're very close together, and very accurate because it's close to the target. This one's very precise but not accurate because they're tightly packed but they're not near the center. These guys are averaging towards the center, so we will call them accurate, but they're not very closely packed, so they're not precise. And then in this case, neither of them are precise nor accurate. When we make measurements, we're going to be using some kind of tool or glassware. And so what we'll want to do when we record those values is estimate the last value between the most precise set of marks. So you're going to do the best you can to read your tool between the last sets of markings and then guess the in between those. So we're going to say, okay, let's say this is inches. This leaf is definitely more than 3 inches, but less than 4. So we'll say it's 3 point something. Now, we don't have any markings in here to tell us exactly where, so we're going to kind of try to break it up the best we can. I would encourage you to use paper to do this. So we could say, okay, that's 3.6-ish inches. We estimated that tenths place there because the ones placed were given in our tool, and then our tenths place was our estimate. If there were markings already, like breaking this up into tenths, then we would then guess the hundredths place. So let's do that again. We have this graduated cylinder, so we know it's between 4 and 5, and then the next set of markings are the tenths. So we know for sure that this amount of water is definitely 4.5. It's not 4.6, but 4.5 if we measure the bottom of the meniscus. And it's up to you on how you choose to read those markings, but I would say it's definitely 4.5. So those are true for certain values, and then our last digit of certainty is, we'll say 4.56 milliliters. Doing it a little bit more, we have this thermometer. It's every single one digit, so 100, 101, 102, 3, 4, 5, 6, 7, 8, 9, 10. So we definitely know that this is about, I'm going to try to do my best to write on this, 103. So we have those digits to the ones place, and so we're going to estimate this last one. Now I might say 103.1. I could also say 103.0. I might say 102.9. Those are all really damn close, and by recording it to the tenths place, we're showing that when we made this measurement, that this was the precision of our thermometer. For this block, we are measuring it. It's between 3 and 4, so it's definitely 3 millimeters. It goes out to the tenths place, so 3.1, 2, 3, 4, 5, 6, 7, 8. So definitely 3.8. And then we can guess our last digit. It'll be different for you versus me, but maybe we might say 3.83. Maybe you might say 3.82. That's all good. That's all perfect. What I care about is not what this value is, but the fact that you recorded it. That's the most important part. When we record digits, we can label those digits as significant because they're part of our measurement. But sometimes when we see all these numbers, we don't necessarily, sometimes it's a little tricky to figure out which digits are actually measured and important versus just placeholders. So the uncertainty of our digits depends on the precision of, the instrument. Oh my gosh, sorry. Instrument being used. We could either, if we took many measurements, we can take an average and find the standard deviation. We could then report that standard deviation with the plus or minus. Or if we make one measurement, we can say, okay, I definitely knew it was 23.4. I'm estimating 5, but I wasn't quite sure if it was 0.40 or 0.50, so I'm going to call it plus or minus 5, and then it's telling us that the true value is definitely somewhere in between there. So that's a kind of a big range for this. Normally we're kind of like plus or minus 0.02 in this case, or 0.01, but that's, I think, being a little bit more on the generous side. When we are reporting these, it depends on our measurement from our tool. And it will either be given to you or you might be actually measuring it in your lab. When we are working with conversion factors, these are exact values. So we're going to say that they have an infinite number of significant digits because they're really never ending. Like the definition of an inch is 2.54 centimeters. There are always 100 pennies and $1, right? So I could say 100.00000 infinity, or I could say 12.00000 pieces in a dozen, right? It's exact. So because they're exact, we don't think about them when we do sig figs. So I, if I were you, would highlight that because that is important. So calculating, or when we're counting sig figs, what we want to do is any non-zero digit is significant. So all of these are not zero. So we have 3 digits, 1, 2, 3, and they're all counting. When we have zeros that are sandwiched in between non-zero numbers, then those are also significant. So these zeros here count. So we have 1, 2, 3, 4, 5 digits. So 5 significant figures. Now leading zeros, so the ones that are in front of our number, are always, are never significant, okay? Because I can say I have 33.5 millimeters, and I can convert that to meters. So I have 1,000 millimeters in a meter, and I can say that's 0.0335 meters. Same digit, so here I have 3 digits. I should still have 3 digits. All I did was change the units. So these 3 count, these 2 do not. So in this case we have 2 numbers and 3 leading zeros, so only 2 digits are significant. So trailing zeros are annoying. Basically the gist is, if there's a decimal, count all the zeros that are after your non-zero digit. Okay, so but if there's no decimal, only count the numbers, these ones basically. Only count those. So here we don't have any decimal points laid out, so the only numbers that will be significant, so, and all of the trailing digits will not be significant, so we only have the 7, so 1 digit. In this case, we have 1 trailing zero, so all of the rest of the numbers will be significant. In these last 3, we have trailing zeros, but there's a decimal point that's written. So once again, here in this second example, leading zeros never count, right? So now we have a decimal point, and then we put a trailing zero, so all of those need to count, so all of these would be significant. Here we have a trailing zero after the decimal, so all 3 digits are significant. Here we have a decimal, and all of those are after it, so those are all significant. But, so that would be 6. But what's really kind of hard is, like, what if you made a measurement and like one of those zeros here were significant and then this one wasn't? How would you determine? How would you write that? Well, the answer is scientific notation. So scientific notation is really nice because any number that is reported with scientific notation is always significant. So when in doubt, write your number in scientific notation, and there will be no questions whether what values are significantly measured and which ones are just kind of arbitrary. So if I was to write this one in scientific notation, I don't have a decimal here, so my trailing zeros would not count. So I would write it as 3.01 times 10 to the third. In this number, I have a trailing zero, but it was after a decimal, so that must be correct. So I have 3.10. I'm going to go back 1, 2. So times 10 to the negative 2. So in this case, so I look at any number before the times 10 to the power thing. Those are all the digits I care about. So 1, 2, 3. 3 significant figures. This one has 1, 2, 3. So 3. So they both have 3, which is awesome. So let's count these guys. So leading zeros never count. Trailing zeros, let's check and see if there's a decimal. Oh, there it is. So it's going to count. So 1, 2, 3, 4. Okay, we have these sandwich zeros, which means that they all count. 1, 2, 3, 4, 5. Oh, this is a conversion factor, so that is an exact number, so we don't even need to worry about sig figs. Here we have our scientific notation, so all of the numbers before this part count. So 1, 2, 3, 4. 4 of those. Now, if I didn't know, if I wrote this out, I would write it like this. 1, 2, 3, 4, like that. And so in this case, they're saying only these ones are significant. So how would we write that if we didn't write in scientific notation? I don't know. It's a great question. Okay. In this case, we have all of these numbers are leading, so none of them are significant, so just 1. In this number, we don't really know. So as it's written, there's no decimal point, so we would say 1, but that is pretty ambiguous. It's not very clear, so we would want to write that in scientific notation if we wanted to be more sure. Scientific notation again, so those 3 leading zeros, never count them, so just the 9s, so 2 digits. Here we have a decimal, so any trailing zeros are good. So we have 5. And then here again we have a big old number, but not quite sure which of these zeros as it's written. Only the 2 and the 1 are significant. So we'll write that like that for now. In this number, I just wanted you to start thinking about what do these scientific notation numbers mean. So if I have a really big number such as 2 million, my exponent is going to be positive. If I have a really small number, then it's going to be it's going to be negative, right? So it's less than 1, it's going to be a negative exponent. Greater than 1, it's going to be positive. So we can determine if I have a really large number, which is greater than 1, then that means we have a positive exponent. If I have a small number, which is less than 1, that means I have a negative exponent. And so is this statement true or false? So if the scientific notation exponent is negative, so if we have a -6 in this number, this means the total number when expanded is also negative. Like we just mentioned, that means that this just means that it is less than 1, not that the number is negative. So the exponent has nothing to do with the sign of the number. It just tells us if it's bigger or smaller than 1. In these problems, we're going to explain whether each of the statements are true or false. So A, you can determine whether a quantity is positive or negative only based on the exponent x in the scientific notation. Well, as we just talked about, that x doesn't tell us about the positive or negative nature of the number. It only has to do with how big the number is. So in this case, that will be, so here we have a negative exponent but a positive number. So we'll say false. If the exponent p, so 10 to the p, is positive, that means the entire quantity must be positive. Not necessarily, right? Because here I have negative 2.8, or negative 2.8 times 10 to the third. So p is positive, it's 3, but the whole number is negative. So if there's a negative in front of the value, then it's a negative, not in front of the exponent. If the exponent n in the scientific notation is negative, that means the entire quantity is less than 1. That is true. So in this case here again, we have this is negative, -2, which means that this number there is less than 1, which we've talked about a bunch. Our last one is when we have a negative quantity, the scientific notation exponent must be negative, and that is not true. So that just, again, that negative exponent just tells us whether it's bigger or smaller than 1, not whether the number is negative or positive. So once we have figured out how to measure these digits, we now need to know what to do with them when we calculate. And this is really important because usually we're using our measurements, like maybe we might be adding 2 volumes together, and if you use different tools that have different amounts of precision, then it's going to be important that you know how to handle those numbers. So when we have multiplication and division, these are nice. They're easiest to calculate, but kind of hardest to explain. So we're going to use the least precise measured value. So that means the number with the lowest amount of sig figs. With addition and subtraction, we're going to find the number that has the lowest amount of decimal places, and that's going to govern it. So we'll start with addition and subtraction. So the first step is to line it up at the decimal point. So we have 23.467, and I'm going to add 313.21. So notice I lined up every number by its digit. The next step is to do the math. So calculate that in your calculator. we get 336.677. So you line them up, you do the calculation, you draw a line to the right of the smallest decimal. So we can see the bottom number only has 2 decimal places, while the top has third. So the bottom number will govern it, so we'll cut it off to the right of that number, which means that we'll report every number in front of it. But we need to see if we need to round that number, and we do, so we'll get 336.68 inches. That's how you would report that. Similar thing here, we have 457 minus 0.68. So we can do that calculation. 456.32, and then we'll cut it off at the lowest number, which is right here, and so we'll just report that as 456, and we do not need to round up. With multiplication and division, it's only 3 steps, so we do the math. We figure out the number that has the lowest number of sig figs. So that means it was the least precise measurement, and we count how many sig figs that was. Then we're going to round our number to that many sig figs. So if I do 3.56 times 4, I'm going to get 14.24 centimeters squared. So I look at these values. This has 3 sig figs, this has 1. So this was our least precise value with 1 digit. So I'm just going to report this to 10 centimeters squared, or because I would want to, only the 1 is significant, I could write 1 times 10 to the 1. So there's just a scientific notation version. Okay, so now I have 2.050 times 5.0, we get 10.25 milliliters squared. And now in this case we have 4 sig figs here, 2 here, so I'm just going to report that as 10 with a decimal, or 1 times 10 to the 1. Oh, this should actually, no, that's right. Okay, and then we'll do milliliters squared, or a similar measurement there. Here we have 45.0 divided by 9, so we get 5.0. We have a 1 digit here, 3 digits here. So we'll write that with just 1. So we would just report 5. Okay, here we have 4.5 feet times 12 inches per feet. So that's a conversion factor. 2.54 to 1 inch. Again, another conversion factor, and then another conversion factor. So we're going to, when we do all that math, 4.5 times 12 times 2.54 divided by 100, we get 1.6716 meters. When we calculate our sig figs, we have 2. Now remember, these conversions are exact numbers, so we have infinite sig figs on all 3 of these. So the lowest number of sig figs here is 4.5, 2 digits, so we're going to write this as 1.4 meters. Our last thing here is just some calculations. So we have multiplying and division. So we're just going to type it exactly how it is in our calculator. And the number we're going to get is 0.65219. So I have 3 digits here, 4 digits here, 5 digits here, and 5 digits here. So the lowest number is 3. So we don't care about leading digits, just those 3 numbers. So we'll report it as 0.652. Okay, in this problem, we're going to line them up, which are already lined up. We do the math, just as written, and you'll get 4.8730. We'll draw our line right here. So we'll round up here, and so we would round up the 8 because of that 7 there, and we get 4.9. Similar thing here. Do the math. Value you get is 0.381367793. Very big number. 3 digits, 3 digits, 4 digits, 1, 2, 3, 4, 5, 6, 6 digits. So the lowest ones are 3. So we don't care about leading zeros. 1, 2, 3. So we'll write 0.81. 0.381 for our value. Cool. Last problem. We'll do the math. We get 120.961. Our lowest digit after the decimal is to the tens place. Be very careful about how you write those numbers. So when we do that, our 9 is our last one, but we're going to need to round. So we'll write 121.0. So this is one of those numbers that we're reporting, and that digit is significant based on the measurements that were made before those numbers were added. So keep that in mind. Next we're going to move into density and energy. So should be good.